Model. So today we see we are going to discuss about the QPSK transmitter and display of digital modulation scheme. And as we know that the digital modulation scheme, where the input bits are going to be as a binary data and carrier component either with respect to amplitude or with respect to wave or with respect to frequency is going to be shifted. So this QPSK itself indicates it's called as a moderator phase shift key. Okay? So it is a key. So since the digital modulation scheme would have already gone through the details and theory in your subject, and with respect to that we will discuss the following points and how to construct a particular step-by-step algorithm, and then we will go for the implementation of the program. Okay. So next one. So today we are going to discuss about the digital modulation scheme, then fundamental of QPSK, constellation diagram and truth table, and block diagram of the transmitter receiver. Once this block diagram is understood, we can go for the implementation of the program. Okay. So first part, as you can see on the screen, the digital modulation scheme. So what is the need of this digital modulation scheme? The need of digital modulation scheme in order to identify the channel capacity. Okay. So here you can see the channel time limit for the information capacity given as either you can write I or you can write C, that is 3.32 times of bandwidth or less than of 1 plus SLN. So that means your channel capacity of the information based on the signal to noise ratio of the received signal and what is the bandwidth available through which the information is going to be transmitted. So this is a quite simple example. You can see in the screen that for a standard telephone circuit, as a signal to noise ratio is 1000 and the bandwidth is 2.7 kHz, and the channel limit is or the information capacity we can calculate with the help of the signal to noise ratio and the bandwidth. So near about 26.9 kbps is the channel capacity or the information available. Okay. Now when we are identifying this channel capacity, next through which particular modulation scheme we are going to transfer. Basically, the digital modulation scheme comes under the multi-leveling signal. Okay? Or you can say it is called multi-level signaling process in which Nyquist criteria plays a vital role. Okay? So Nyquist criteria plays a vital role. Now, as we know that when we are converting the analog signal into digital, there are certain steps are available. First, you need to sample it, then you need to quantize it, and then you need to represent those quantized levels with certain binary bits. So the number of binary bits are interrelated with the levels. So L is equal to 2 to the power n is the basic relationship. Most probably this relation everybody knows. The number of levels L is equal to 2 to the power n. Okay. So 2 to the power n is the number of bits and n is the number of levels. So here you can see log base 2 n is equal to 5. So that means the number of bits are 5 and the number of levels are 32. So each level is represented with 5 bits. So representation will be identified according to the number of levels, and these levels are going to be represented in the binary data. What is the use of this binary data? The binary data can be transmitted through a particular channel towards our receiver. Now, in order to transmit a message signal, we require modulation scheme. If it is a digital modulation, then we can go for QPSK. We are having two modulation schemes, as you can see, that binary modulation scheme and M array modulation. So binary modulation schemes are ASK, SSK, and CSK. And M array means M number of elements are there, then modulation scheme are called as QPSK and QM. Moreover, it is 8 PSK, 16 PSK, 16 QM, all are available with. Okay. So basically in today's discussion we will focus on QPSK, then we will discuss about the binary modulation scheme and how this modulation scheme helps us to transmit the signal towards from transmitter and the receiver end. And we are going to construct the transmitter part, how the modulation happens, what are the features are there, that it is. Okay. So here in this figure you can see the digital word of the bits and the information are represented with this particular bit. Okay. So the discrete levels are represented with the binary data, which is transmitted, and at the receiver end we can extract the information by converting the digital value into the analog signals. Okay. The second part, you can see this is the fundamental of QPSK. In QPSK, basically there are four possible combinations we are going to transmit. So four possible combinations means two binary bits we are going to transmit. So at a time 2 bits means the combination either will be 0, 0, 0, 1, 1, 0 and 1, 1. QPSK, or it is called M array encoding scheme, where n is equal to 2. So at a time 2 bits are going to be transmitted at different phase, and the two possible combinations are separated at an angle of 90 degrees. So this is called Fourier Decision key, and these two bits are called the die bit. Okay? And each bit die bit code generates with four possible output phases. So one is 45 degree you can assign, then plus 90 degree, then 135 will come, then you plus 90 degree, another phase it will come, that is minus 45, and again if you add at 90 degrees, then it will come at minus 135, or you can subtract with 360 degrees, you will get your angle. So four quadrants we have the four possible combinations. So four possible quadrant means, so let us consider this is the quadrant. So this is one quadrant, this is second quadrant, okay, and this is third quadrant, and this is fourth quadrant. Okay, so basically the fourth quadrants are available. So here one pair is available, here one pair is available, here one pair is available, and in this particular quadrant one pair is available. So in this, either we can represent this one with E1. Let us consider this value E1, or energy content, you can say in one axis you can put a sine wave, in another axis you can put a cos wave. If both are possible, then the first quadrant will have 1, 1. Similarly, this will have 1, 0. This will have 0, 0, because here the negative quantities are available. We will see how this happens, and here we will see this 0, 1. So like this possible combinations are available. If this is represented with 45 degree, then plus 90 degree you will get 1, 0. So that is at 135 degree. Similarly, another if you add 90 degree you will get minus 45 degree. So this is minus 45, and again it is minus 1. Okay, so there are four quadrants are separated with an angle of 90 degree. Done. So now QPSK signals is also called as quadriphase PSK, or 4 PSK, or 4 square, and the transmit of 2 bits are required. And when we are transmitting this signal, we require 2 carrier components. Remember that. Okay. So the general equation, as you can see, SI of P is equal to the power of 2 by P cos of 2 pi of Ct divided minus 1 pi by 4. So pi by 4 means it is 45 degree. Means first, if you assign an I is equals to 0 or I equals to 1, then 2 minus 1 is 1, then pi by 4. So phase shift will identify the 45 degrees. Then if you add, substitute I is equals to 2, then 2 into 2 is 4, 4 minus 1 is 3, so it is 3 pi by 4. That means if you add pi by 90 degree to your pi by 4, you will get your 3 pi by 4. Similarly, the representation of these signals are going to be identified. Here D is called as a symbol duration, and for the representation of this QPSK signal we require two basis functions, one in phase and one anti-degree phase. Suppose if in phase component we are considering cosine, then your 90 degree phase shift will become as a sine term. So why I am using these two orthonormal functions? Because in this QPSK, as you people might know about that, while dealing with QPSK, we divide or we segregate or we demultiplex the input data stream into even bits and odd. So odd bits is provided with a cos term and even bit is provided with a sin term, or vice versa. Anyone you can choose. And the representation will be, if you expand this cos A and cos B form, you will get cos A cos B plus minus sin A sin. So here you can see that it is in terms of cos A cos B, and here it is in terms of sin A sin. So these are the basic equation for the QPSK field. And here you can see that cos 2 pi FCT is the orthonormal function of C1 of t, and here you can see sin 2 pi FCT is the orthonormal function of C2 of t. So you can combine these two at the end and you can generate the QPSK signal. Okay. Next, this is the fundamental of your same QPSK, how we are going to identify. One is in phase and one is quadrature. In phase component reference to the oscillator, that means if the even component is identified to provide the in phase, means cos signal to it, and if the odd signal is identified we provide quadrature, that is Q 90 degree phase shift you can provide, that is the sine term. While dealing with the block diagram, you can understand why I am using this I bit and Q bit. Okay. So whenever there is a logic 1 is identified, that means that the potentiality you have to assign as plus 1, and when the logic 0 is identified you have to assign minus 1. So two phase will be identified. Okay. And according to that, your sine and cosine R terms are multiplied with each other, and at the end you have to add those. So this is the constellation diagram what I have drawn previously. So QPSK Phasor constellation diagram is the basic representation. In the right hand side you can see the binary input and QPSK output. So if it is 0 0, that means the angle is minus 135, it is third quadrant. Okay? And if it is 0 1, it is minus 45, that is fourth quadrant. If it is 1 0 plus 135, that is the second quadrant. And if it is 1 1, then it is plus 45, that is the first quadrant. So we are using the 4 possible combinations with the help of 2 binaries. So 4 possible combinations is 0 0, 1 1 0 and 1 1, and assigning the angle with respect to the presence of the quadrant. In first quadrant both the potentials are high, so that means it is 1 1 and assign an angle of 45. So here you can see that sine term plus 45 and cosine term plus sine term. So cosine means it is provided with Q quadrature, and I means it is in phase component. So 1 1. When Qi is 1 0, that means 1 is provided with cos, and this 0 means minus 1, so it is minus sin omega. Okay. Now here you can see 0 0, both are in minus minus, so it is minus cos omega ct minus sin omega t. And here it is 0 1, that means 0 means minus 1, so minus cos omega ct, 1 means plus sin omega. So this is the constellation diagram. Here the axes are divided with respect to cos omega ct and sin omega ct. So these are the two signals, two orthonormal functions. In some of the books it will be written in terms of phi 1 of t, okay, and here it is phi 2 of. So depend upon that representation, we can represent our values. So either it will be written in phi term or phi term, or this is in terms of phi 1 or cosine term. So this is the constellation diagram through which we can understand the representation of binary. So here 2 bits are going to be identified, so it is called the binary, and 2 bits means 4 possible combinations, 0 0, 1 1 0 and 1 1. So depend upon that the angles are assigned. Okay. Next, the block diagram. So this block diagram you can understand that. So here AB is the binary. So here I have considered the binary. So this binary is need to be split out. So it is given to the splitter. Okay. So upper part is to consider as odd. This is odd bit. Lower part you can consider it as an even. Okay. So in odd also we will have binary bit 1, binary bit 0. If binary bit 1, you have to assign plus 1. If binary bit 0, you have to assign minus 1. Okay. Then the odd is multiplied with the first orthonormal function, that is cos omega. Yeah? Then even is multiplied with sin omega. Here it is in place of cos, the sine. Because why it is sine? Because it is cos omega z passed through a 90-degree phase shift, it will become a sine term. So this sine is multiplied with the given bit and we will get one output. Similarly, here the odd is multiplied with your cosine signal and modulated output is available here. Let us consider x1 and here it is considered as h. Now at the end what happens? x1 plus x2 is called as the QPSK. In that equation you can see that x1 plus x2 is equals to QPSK. So if you add these two signals, we will get our QPSK. So odd bit and even bit. So odd bit is provided with one orthonormal function, even bit is provided with another orthonormal function. One is in phase and one is out of phase. So here you can see in phase means I channel, that is with cos omega c, quadrature channel, that is with respect to sin omega c. So this is with respect to even, this is with respect to odd. And at the end what happens? You have to add these two, we get your QPSK. So even plus odd, the resultant we will get as a QPSK. Okay, and then we can transmit over a particular channel. So this is the basic block diagram of QPSK transmitter and with respect to the block diagram. Then with the help of receiver what happens? When we receive the signal, it will be provided to both the inputs where the cosine signal is provided to this mixer and the sinusoidal signal is provided to this mixer. So this is the carrier equation. Okay? So cos omega c is multiplied with this and sin omega c is multiplied with this and passed to an LPO. So that means this is nothing but a coherent detection. Up to this much is called as coherent detection. So upper part if you are considering for the detection of odd, then the lower part will be considered as an even detection. So this is even and this is odd. So odd detection will be this. Now if the output of this LPF, okay, so the output of this LPF is greater than the precision level. Suppose here I am considering lambda 1 is one threshold value and here I am considering lambda 3 is our one threshold value. Well, now if this threshold value is, let us consider 0.5. Okay, 0.5. My threshold value is 0.5. So if the output of this, okay, if the output of this particular point, so if my let us consider this is A and here I am considering this. Now if your A is greater than 0.5 then the binary will be 1. Okay, and if A is less than 0.5 then binary will be 50. So this is the logic. This is the decision device will be. Similarly, if B is greater than lambda 2 then binary will be 1. If B is less than lambda 2 then binary will be 2. And at the end what you have to do? At the end you have to add all these multiplex signals and recover just the identity. That means this odd bit and even bit, if you add all those things, you can recover your original signal. So this is the logic behind for the reconstruction of the received QPSK signal and we can extract our binary data. So this is the QPSK receiver problem. Next we will discuss about the algorithm through which we can proceed for the numerator. Okay. So this is the algorithm part. So first for modulation, what are the requirements are there? The requirement is first of all you have to generate the carrier. Okay. How many carriers? 2 carriers because 2 orthonormal functions are there. One in phase and one quadrature. In phase means sin omega c, quadrature phase means cos omega c. Anyone you can consider. If you are considering in phase as cos, okay, quadrature must be sin omega c. Then you have to start the for. Why? Because the for loop will identify depend upon the length of the binary bit. How many binary bits we have to hold, and that for loop will continue up to the length of that binary input data. Suppose I am giving 5 input data, that means the for loop will continue for the 5 times. And how that 5 times will happen? First it will identify the even bit, second it will identify the odd bit. Then once it is identified as an even bit, assign multiply with the any of the orthonormal function, either cosine term or sine term. Similarly, when you are identifying the even term, multiply with cosine term or sine term, depend upon the choice. Okay, and then generate the binary data or the message signal in bipolar, because here we are identifying binary bit 1 and binary bit 0. Okay, but binary bit 1 must be represented with +1 and binary bit 0 is represented with -1. Then multiply the carrier 1 with the odd bit, that I have told you. If it is carrier 1, then multiply with odd bit and the message signal with the carrier 2 with the even bit. Okay, so if it is odd bit, multiply with cos. If it is a even bit, multiply with the sine term. Then perform the addition at the end. According to that block diagram, you have to add the even part and the odd part. So once it is added, QPSK modulated signal is determined. And then once it is output is available, you need to plot. So you have to plot the QPSK signal. And then you have to end up the for loop, and then you have to plot the binary data with that. So these are the modulation steps or the algorithm for the QPSK modulation. Similarly, when we are going for demodulation, here also we need to recover the original signal, that is the binary data, from the received QPSK system. Here also again we are going to use the for loop. Why? Because according to the for loop only we can extract the data. Okay. Now perform the correlation of QPSK with quadrature carrier with 2 decision levels. Yes, there are 2 decision levels are there with a variable of x1 and x2. As I have told, if x1 is greater than lambda 1, that means binary bit 1. If x2 is greater than lambda 2, binary bit 1. If it is less, then binary bit 0. And at the end what happens? You have to make a decision. Okay. Now here what happens? If x1 is greater than 0 and x2 is also greater than 0, that means combination is 1 1. Here you can see x1 is greater than 0 and x2 is greater than 0, so combination is 1 1. If x1 is greater than 0 and x2 is less than 0, that means lower one is less than 0, then possible combination is 1 0. Okay. One more combination, if x1 is 0 and x2 is greater than 0, then it is 0 1. And the last combination, if x1 is 0 and x2 is 0, then my choice will be 0. So with the help of this, we can reconstruct our original modulating system. And then you have to end the for loop and you have to plot the demodulated data. Okay. Now next we will see how this algorithm we are going to implement, and for the modulation as well as for the demodulation function. Okay. So here is the logic behind how we are going to implement the QPSK signals. So first you can see here you have to generate 2 carriers. So QPSK modulation, CLT, clear all, close all, solve it, you have to generate the quadrature carrier. So quadrature carrier in QPSK we require 2 orthonormal functions. First we have to define those 2 orthonormal functions. So for that, the TB is the time period for the binary bit, this one. You can consider 2 also. T is equals to 0 to TB by 2, 2 to TB by 100 to TB. This is the time period divided with 100 dB. Means from 0 to 1, it will be divided with 100 small units. Okay. And the carrier frequency I have set as 1. You can take 10 also. So first I will write the equation as C1 square root of 2 by TB cos of 2 by FTP. Okay. Then C2 is square root of 2 by TB sine. So this is the in phase. Okay. In phase carrier, and this is quadrature phase carrier. So like this you have to analyze. Like this you have to define. Okay. So this is the in phase component and this is the quadrature phase component. So we have generated 2 carriers. Okay. Next we have to generate the message signal, and we have to multiply that message signal with the this C1 and C2 to segregate. So here I have considered n is equals to 8, means number of binary bits are 8, and random value. So here I have considered m is equals to random of 1, n. So randomly it will take 10, 10 or 11, like that 8 possible combination of binary bit it will provide. Okay. The random function itself indicates that it will provide the binary bits with its own combination. Either it is 10 10 10 or either it is 11 0 0 0 0. It depends upon that random value. Okay. Then T1 is equals to 0 and T2 is equals to T2. So these are the two time periods through which we can through which we can go for the for loop conditions. So this for loop is I is equals to 1 is to 2 is to n minus 1. So that means the n is 8. Okay. The total iteration will be 8 times because we are considering number of input data is 8. So I 1 is to 2 is to n minus 1. Then t is equals to t1. Then tb by 100 is to t2. So that means the total time period will lie between 0 to t. You have to assign that particular time period. Okay. And here, if m of I is greater than 0.5, you have to decide whether it is binary bit 1 or binary bit 0. So here the condition is if the m value, okay, if the m value is greater than 0.5, that means binary bit 1. Here you can see binary bit 1. Now once this binary bit 1 is identified, you have to assign the value in a matrix form, because here whatever we are discussing, all it is presented in matrix representation. Okay. So m suffix s is equals to 1 of 1 comma length of t. So t is how much? T here we have considered that t is considered as the time period or the length of the function. Okay, t is equals to this one. So once 1 comma that much. Else, if it is less than 0.5, assign 0. If it is assigned 0, that means you have to assign minus 1. You have to assign the potential. Bipolar you have to represent. So for bipolar you have to provide ones of. Okay. Similarly, if it is 0, you have to assign minus 1. So here it is minus 1 into ones of length of. So then you have to end it. So this particular whole loop from this for to this end, it is used to generate the 8 binary data in a bipolar manner. Bipolar means it will have the polarity of +1 and minus 1, assigning the plus value and minus value. Okay. Once this binary data binary plot is done, then we have to identify the odd value and even value. Once this odd value is identified, we have to multiply with the in phase Phasor component, and if it is even is identified, we have to multiply the quadrature phase component. So that you can see here. So odd bit modulated signal. So odd signal of I is to odd value C1 into m suffix s. So m suffix s you can see either this value or this value. It will be multiplied with C1. If mi, we have to increase the iteration step by step. So m of I plus 1 greater than 0.5, that means it will be identified as 1 and ones of length of t. Else it is 0, then 0 means it is minus 1 into length of t. Okay. Similarly, if it is an even bit, you have to multiply C2 to m suffix s. This is our message signal. So m suffix s. Then you have to add the QPSK signal by taking odd value and the sign value as n. So QPSK is equals to odd underscore signal plus even underscore signal. Then you have to plot the QPSK. That means first you have to identify odd, then you have to identify even, then you have to add those two signals, then you have to plot this. Now here subplot you can identify, you can put 3, 2, 4 or 1, 2, 3 depend upon the matrix size. So here the matrix size is 3 cross 2 and the fourth is the position. Okay. Then plot t, QPSK I of all value, title it QPSK signal, x level is time, y level is s of. So this is all about the modulation part. Now once we have generated the QPSK signal, we need to demodulate. Okay. So here it is a demod. This is the part of your modulation part. Then you have to grid on it, or you can use grid on, or you may not use grid on. Hold on it. Then T1 is equals to T1 plus Tb plus 0.01 and T2 is equals to this time. So T1 and T2, these are the two time periods within which the binary bit is going to be identified. Then you have to end the loop and you have to hold off. Hold off means it will stack to that particular point. Then you are going to plot all these signals. You have to plot carrier signal, you have to plot modulated signal, you have to plot the message signal, you have to plot the binary signal. So subplot c comma 2 comma 1 stem it means binary data in a stem manner. Title it binary data x label, y label, 3 dot. Then subplot it. Okay. Then you have to plot the carrier signal. The two carriers, one is carrier 1 and one is carrier 2. So plot t comma c1, title it. Plot c comma d2. Assign the subplot values. So this is the representation or the plot of binary data with carriers. Then once it is done means next we can identify the extraction value. How we are going to identify the expected value? How we are identifying x1 and x2? So x1 is the output of correlator. Means when we are extracting the information, we need the loop. So for loop is used. So here you can see t1 is equal to 0, t2 is equal to tb, and the for loop will continue up to I is equals to 1 to n minus 1. Then the same time period what we have defined in the previous one in our modulation, here also time period is this. So that means it is called as a coherent. Here we are synchronizing the time period. So it is called coherent detector. So what is our x1? x1 is a sum of c1 into QPSK and x2 is sum of c2 into QPSK. So this is a dot multiplication means position to position multiplication. So once x1 and x2 we have got, then we have to decide whether x1 is greater than 0, x2 is greater than 0. If this is satisfied, then binary bit is 1, 1. And if it is x1 is greater than 0, x2 is less than 0, then we have to decide then binary bit is 1, 0. Similarly, there are 4 possible statements we have to define to extract the information. So here you can see decision of the device is done as if x1 is greater than 0 and x2 is greater than 0. So both are greater than 0 means binary bit 1, 1. So d mod of I is 1, d mod of I plus 1 is 1. So I plus means it is increasing 1. So there are 2 bits. If it is 0, 0 greater than 0, so it is 1 and 1. If it is x1 is 0 and x2 is less than 0, so that means it is 1 and here it is 1 and then, and else if x1 is less than 0, x2 is less than 0, then both are 0, 0. And last condition is what? x1 is less than 0, x2 is greater than 0, so it is 0 and 1. And you have to end the loop. And the same time period what we have decided here, the same time period we are going to use here also in order to synchronize the time. Remember this. So if you are not synchronizing means it is not a coherent detector. It will become as a non-coherent. Okay. So once this is end, you have to plot it. Then you have to identify the demodulated signal. So if you make the stem of demodulated, which will be same as your input data. Okay. Title it QPSK. Demodulated signal, x label is n, y label is b of n and 3 of. So this is the basic steps through which we can see the QPSK modulation and demodulation. Okay. Next we are going to implement this whole thing in our MATLAB environment. So 1 minute. So 1 minute. So now we are going to implement the program what we have discussed now in the MATLAB environment. For that I have opened the Internet Explorer and which online we can execute. So step by step we will see. Let me open the online MATLAB compiler. This is my online MATLAB compiler. So as I have discussed in the last class that you go open your account in the MATLAB online MATLAB. and it will provide a domain to which we can execute our code. But the limitation is that here only the inbuilt functions are means suppose if I am using the modulation, if I am using the demodulation points, then it may take or it may not, because it is user defined, it's having a Phasor for some only one few commands are executed, but the constants and other functions may not. So step by step we will see. So here you can see that already I have given the instructions as per the program what I have discussed now. First you can see that yes, the modulation, it is CLC, clear all, generate, first you have to generate the signal, that DB1 and DB10, then you have to identify two carrier components C1 and C2, you have to fix the time period for T, you have to give the frequency as you can put this FC as 2, 10, whatever it is, I have given it as 1. Then here I have given number of input binary data is 8, you can give 10 also, you can give 4 also, depends upon you, and you have to generate the sequence. So here n is equals to random of 1, n is there. So 1, n means 1 with n number of columns will be there. So if it is 8, 1, 8 means 8 number of columns, and first row all the binary bits will be in a random number. Whether it is a 101010 or whether it is 11000, it depends upon the randomness of the selection. Then you have to fix the two time period, T1 as 0 and T2 is T. Okay, so you synchronize the time period. Then you have to start the for loop through which we can assign the binary bit. If it is 1 is identified, that means plus 1. If it is binary bit 0, is to assign minus 1. So this is the equation, or this is the if statement which justify or which will assign if mi of 0 or m of I is greater than 0.5, that means it is binary bit 1. If it is binary bit 1, that means you have to multiply plus 1. If it is else, it is minus 1 is multiplied. So else m of I is 0 multiply minus 1. So this is the generation of a from this for loop to up to this much. Okay, it is a generation of a bipolar signal. Okay, bipolar signal. Now once this bipolar signal is done, then we have to go for the identification of even bit and odd bit. So once this odd is identified, that C1 is multiplied with the S suffix signal, M suffix S, whatever the signal you have got, whether it is binary bit 1 or binary bit 0. So if it is odd signal, multiply the orthonormal function C1 of T. If it is even, then multiply C2 of T. Okay, so it is C1. So if m of I plus 1 greater than 0.5, then m of I plus 1 is 1. Then m of S is plus 1. Else it is 0 means minus 1 you have to multiply. Similarly, even bit you have to generate by only substituting C1 as C2. Once even signal is generated, QPSK signal will be generated by adding odd signal plus even signal. So here QPSK signal is generated, that is odd signal plus even signal. Now once the signal is generated, you have to plot it. Okay, so here I have to subplot 3, 2, 4, plot T, QPSK, I with respect to all the value, title it, Y level, X level, read on, hold on, and the time period. You have to synchronize the time. Okay, and then you have to end off. Now once it is done, modulation part is done. Next you have to represent the binary data, you have to represent the carrier component. So here I have given the subplot 3, 2, 1 stem of M. So stem of M means binary data, it will represent directly. You have to put the title as the binary data bits and X level and Y level. Then subplot 3, 2, 2, C, and the title it with respect to subplot. Once this leveling of the carrier 1 and 2 is done, then you can go for the C multiplier. Now once you have set the T1 and T2 with the time period 0 and T, same time period also here will be defined, because we are going to extract the information with the help of coherent detection. Remember that here we are deciding with respect to the coherent detection. So the coherent detection is done with respect to the correlator, that is x1 is equal to sum of c1 dot multiplication of QPSK, then x2 is the sum of c2 with the QPSK received signal. Then decision will be decided that if x1 is greater than 0 and x2 is greater than 0, then it is bidirected 1, 1. So demodulation of I is 1, demod of I plus 1 is 1. Okay, else if it is 1 and 0. So these 4 conditions we have to set. So this is the 4 else if conditions we have to set in order to extract the binary data. And the time period is also need to be synchronized. The same time period what we have used during the modulation, same time period we are going to use for here. Then you have to plot it, stem, the demod, whatever the signal we are getting, you have to demod it, and if you write stem, that means it will extract the same signal what we have transmitted, and that is called QPSK, demodulated, X level, Y level, plotted and read off. Okay. Now once this is finished up, save it. Okay. Already I have saved with QPSK.m, and then go for its run option. So once it is run, the executed value will be identified and the figures will be generated with all the parameters like input data bit, then 2 carrier component and 1 QPSK signal. So this is the first binary data. So what I am going to use, I am going to save it. So here there is an icon called save. Okay. So here you can see it is an export. Either we can export with PDF or PNG, anyone. So export to PDF, can save online. I'm giving my name because at the end you have to show the outputs and all. Save PDF, dot PDF. Once again export. Here I will save as save. I have saved. Now in this window, left hand side you can see the video and you can open it. So here you can see that my binary data first is 1010, all it is available, so it is 11, then 0, 11, then 0, 0 and 1. So these are the 8 data bits are available with the binary representation. So this is the binary data. Then 2 carrier signal we have defined. One is carrier signal 1, one is carrier signal 2. Then QPSK signal is generated. Every 90 degree the carrier changes. So 0 to first carrier is follows this particular path. Okay, and second one is follows this particular path. And this QPSK is generated with the help of this binary data. When the binary data you have to segregate with even bit and odd. So if you identify the odd position, this is the first one, this is the third one, this is the fifth one, this is the seventh one. So this is odd. 1, 2, 3 and this is 4. So 4 are odd, so it will be multiplied with cos term. So this is the first one is cos term. Then evenly, this is second, this is 1, this is 2 and this is 4. So there are 4 even parts. So second is our sine. So you can see that the sinusoidal waveform is generated. And when you are extracting the information, your QPSK demodulated signal is quite similar to your binary data. So like this you have to execute and you have to show this output for the QPSK modulation and demodulation. So this is the basic concept behind the QPSK modulation and demodulation. For example, if I am changing the frequency, suppose if it is 10, let us consider, okay, save it. If any changes you are making in the program, just save it and then once again you run it, okay, and you will get your figures according to the given inputs. You will see that. One. So here you can see that let me save it first. So please see that my carrier frequency changes. So one I have considered with respect to cos, one I have considered with respect to sine, and here this is our QPSK signal. Since the frequency is very high, we have put as 10, so the time period is less between these. So you can see that the time period is less. If I am taking frequency component as less, time period will be high. So once again we will see if there is a change with respect to frequency component. Okay, so if it is, let us consider 0.5. Okay, we have took 1. Let us consider 0.5. Save it and then run. The frequency component will little bit stretch out with it, so time period will increase. So here you can see that figures are like. So let us consider 2 or 1, whatever it is. Now let's see that sine and cosine wave with the frequency of 2 it will show, and our QPSK signals are also distinct. So here you can see the distinct frequency. This is the carrier frequency 1. This is a cosine signal. This is the sinusoidal signal, and this is my QPSK signal, and this is a demodulated QPSK signal. So this is the basic program through which we can extract the modulated part as well as the demodulated part, the transmitter end and the receiver end. Because the transmitter end basically modulation takes place, and at the receiver end the demodulation takes place. At the receiver end we need to see whether my QPSK data is same as our binary input or not. If it is same, that means it is called as a, and in this program we have used the coherent detection. Okay, here we have used the coherent detection. You can go for envelope detection also, but the logic you have to write for that. Here we have used the coherent detection method. Okay, so this is the QPSK transmission and reception. Next class we are going to discuss about the modulation schemes and the pulse code modulation. Okay, so only 2 experiments are left. If possible, I will discuss with respect to BPSK also. But in BPSK there are few inbuilt functions are available, but free editor or free online resources for here, it may provide, may not provide. I will try it and we'll discuss in the next class. Okay, till then practice this numeric practice this program. All the things are available. Go through this equation and as well as this program step by step and execute it and get the outputs better, and start identifying the variations. If you vary the frequency of the happen, if you vary the amplitude what happen, you can give +1 -1. I have given +1 -1, you can give +2 -2 also. It depends upon you. Okay, so depends on that. Your waveform will be identified and you can get this sort of nice waveforms. Okay, till then, thank you all. So next class we will continue.